What is the specific problem addressed by the proposed method in the paper?
The specific problem addressed by the proposed method in the paper is the lack of robustness in fact retrieval by large language models, LLMs, due to context hijacking. The paper focuses on how LLMs can be easily misled by varying contexts, leading to incorrect outputs even when the factual meaning remains unchanged. This phenomenon of context hijacking highlights the fragility of LLMs in accurately recalling facts based on the given context. The paper systematically demonstrates this issue by manipulating contexts to influence LLM outputs, showcasing that accurate fact retrieval does not solely depend on the semantic meaning of the context. The proposed method aims to deepen the understanding of LLMs by viewing them as associative memory models, where tokens in contexts guide memory retrieval, even if the associations formed are not semantically meaningful. Through experiments and theoretical analysis, the paper delves into how transformers, fundamental components of LLMs, tackle memory retrieval tasks, and the role of latent concept association in modeling fact retrieval.
How does the proposed method work, and can you illustrate it step by step?
The proposed method works by focusing on fact retrieval in large language models, LLMs, and exploring the phenomenon of context hijacking. The method aims to understand how LLMs retrieve facts and memories based on the context provided. The first step involves demonstrating context hijacking, where LLMs can be misled by varying contexts, leading to incorrect outputs without changing the factual meaning of the context. This phenomenon challenges the robustness of fact retrieval in LLMs. Next, a synthetic task called latent concept association is introduced to model memory retrieval in LLMs. In this task, the output token is closely related to sampled tokens in the context, with similarity measured through latent semantic concepts. The method then delves into how a one-layer transformer, a key component of LLMs, can handle this memory retrieval task. The transformer accomplishes this task in two stages. The self-attention layer gathers information, while the value matrix functions as associative memory. Theoretical analysis is conducted to understand how the transformer solves the latent concept association problem. The method proposes a hypothetical associative memory model where self-attention aggregates information and the value matrix aids in memory retrieval. The study also investigates the role of embeddings, showing that training embeddings is crucial in the underparameterized regime to achieve better recall accuracy. Furthermore, the method explores the importance of the value matrix and its associative memory structure. Experiments are conducted to compare the effects of training versus freezing the value matrix, and to examine the alignment between trained and constructed value matrices. The significance of embedding training and the formation of specific embedding structures in the underparameterized regime are also studied. Additionally, the role of the attention selection mechanism is analyzed, showing how attention can filter out noise and focus on relevant information in the context. In summary, the proposed method systematically investigates context hijacking, introduces a synthetic task for memory retrieval, analyzes the transformer's approach to solving memory recall tasks, and explores the importance of the value matrix, embeddings, and attention mechanism in LLMs.
What are the practical benefits of using the proposed method over existing alternatives?
The practical benefits of using the proposed method over existing alternatives lie in the enhanced understanding and improvement of large language models, LLMs, specifically in the context of fact retrieval and memory recall. The method introduces a synthetic task called latent concept association, which allows for a more nuanced measurement of similarity in a latent space of semantic concepts, rather than direct associations between observed tokens. This approach helps in modeling how transformers, fundamental components of LLMs, can tackle memory retrieval tasks with varying context distributions. The method demonstrates that transformers can accomplish memory recall by utilizing self-attention to gather information and the value matrix as associative memory. Additionally, the method sheds light on the importance of training embeddings in the underparameterized regime, showcasing how embedding structures capture similarity within the latent space. Furthermore, the method highlights the role of the attention mechanism in selecting relevant information, aiding in noise reduction and focusing on informative conditional distributions. Overall, the proposed method offers a deeper theoretical understanding of how transformers operate in memory retrieval tasks, leading to potential advancements in developing more robust and efficient LLMs.
How was the method validated or tested in the paper?
The method in the paper was validated and tested through a series of experiments on synthetic datasets. The experiments aimed to evaluate the theoretical claims made in the paper regarding the importance of the value matrix, the necessity of training embeddings in the underparameterized regime, and the role of the attention mechanism in selecting relevant tokens. The experiments compared the effects of freezing versus training the value matrix, replacing trained value matrices with constructed ones, and examining the alignment and low-rank approximations between them. Additionally, experiments were conducted to assess the impact of training embeddings in different regimes, and to study the embedding structures formed in the underparameterized regime. The experiments also investigated the attention selection mechanism by analyzing how attention patterns can filter out noise and focus on informative conditional distributions. Overall, the experiments provided empirical evidence to support the theoretical findings and insights presented in the paper regarding the functioning of transformers in memory retrieval tasks and latent concept association.
What were the specific results achieved with the new method?
The specific results achieved with the new method include the demonstration of the importance of the value matrix in maintaining a high memory recall rate, as freezing it can lead to a significant decline in accuracy, especially when the context length is small. Additionally, experiments showed that replacing the value matrices in trained transformers with constructed ones did not significantly decrease accuracy, indicating functional similarity between the constructed and trained value matrices. Furthermore, the constructed value matrices and the trained ones shared similar low-rank approximations. In terms of embeddings, it was found that training embeddings is crucial in the underparameterized regime, where embeddings exhibit certain geometric structures. The experiments confirmed that embedding training is required when the embedding dimension is smaller than the vocabulary size, while it is not necessary in the overparameterized regime. The study also revealed that trained transformers in the underparameterized regime exhibit a relationship between the average inner product of embeddings for two tokens and their corresponding Hamming distance, aligning with a specific linear relationship. This embedding geometry can lead to low-rank structures, as evidenced by eigengaps between top and bottom singular values in the spectrum of the embedding matrix. Lastly, the role of the attention selection mechanism was explored, showing that attention can filter out noise and focus on the informative conditional distribution by selecting tokens in the same clusters based on specific settings.
What are the limitations or drawbacks of the proposed method?
The limitations or drawbacks of the proposed method include the necessity of a value matrix for maintaining a high memory recall rate, especially when the context length is small. Freezing the value matrix as the identity matrix can lead to a significant decline in accuracy. Additionally, while the constructed value matrix and the trained value matrix functionally align and share similar low-rank approximations, there may still be challenges in fully capturing the complexity of memory retrieval tasks. Another limitation is the requirement for embedding training in the underparameterized regime to achieve better recall accuracy, which may add computational complexity and training time to the model. Furthermore, the theoretical analysis and experimental results focus on simplified models and synthetic tasks, which may not fully capture the intricacies and nuances of real-world language understanding and memory retrieval tasks. The proposed method also assumes certain idealized conditions, such as orthonormal basis embeddings and specific attention selection mechanisms, which may not always hold true in practical applications. Lastly, the theoretical framework and experimental setup may not fully address all potential sources of error or misclassification in memory recall tasks, leaving room for further exploration and refinement of the proposed method.